Welcome to our discussion on applications of integration. More specifically, we're going to talk about volumes. And before we get into volumes, we have to kind of remember some of the key things that got us here. First of all, it's the fundamental theorem of calculus. It's called the fundamental theorem of calculus for a reason because it's pretty fundamental to all the stuff that we are going to be doing. So we just need to remind ourselves, that we can find the area under a curve, and those are related to antiderivatives and all the fun stuff that we learned with the fundamental theorem of calculus. We also need to remind ourselves some of the techniques of integration, right? We might have to do some substitution or integration by parts. And lastly, all of these things are going to build on the idea of doing Riemann sums to find area under curves. So we would just kind of refresh our memory with those types of things. So to find volumes of a solid, we have to go through some of the same type of problems that we did when we had to find area. We can come up with this kind of intuitive idea of what the volume means. We can, slice it up into pieces and do those types of things. But it's going to be a very similar process to finding area, where we have to end up using calculus to get an exact measurement instead of an approximation with kind of these Riemann sum things. So let's start with a very simple solid. We call this a cylinder, or more precisely, it's a right cylinder. Now, you might think of a cylinder as something that looks like a can of soup, like a cylinder in a car engine, and that's a right circular cylinder. But a cylinder, by definition, is any geometric shape where it has a base and a top that are parallel surfaces, and then the sides are perpendicular to it. So what you can see here is B1, right, is the base. B2 is another surface that's the same shape and it's perpendicular to it. I'm sorry, parallel to it. And then the sides, this curved side and that straight side, are both 90 degrees, right? They're perpendicular to the top and bottom. So that's a right cylinder. So basically, all of these, that surface to the side surface makes a 90-degree angle. The top surface to the side surface always makes a 90-degree angle. And when we have anything of that shape, the volume is always very simply just the area of the base times the height. And in fact, if you remember that, it will help you figure out or memorize formulas for other shapes that we know. Like here we have a right circular cylinder, right? Kind of the cylinder that we think of when we hear the word cylinder. And we know that its formula is pi r squared times height. But what's pi r squared, right? That's just area of a circle. So hey, look at that. That's area of the base times the height. And then, of course, we all know how to find the area of a rectangle. It's length times width times height. But what is length times width? That's the area of that base, right? So area of the base times the height. So you can see that that formula always holds for any type of right circular cylinder. So if we wanted to find the volume of any solid cylinder, we just need to cut it into a certain number of pieces. We can say S number of pieces and think of those as cross sections. You just need to make sure that when you're cutting, you have to cut in a direction so that the slices are all the same shape. So for instance, with this thing, you wouldn't want to cut vertically, because if you cut vertically, they'll all be different shapes. But if you cut horizontally, right, every slice would be the exact same shape as the base. So that's going to be kind of the key to when you're slicing these different shapes, is to make sure that you're always slicing such that the shapes are always the same shape. Now they might be different sizes, like this one, right? So you see, if you do a vertical slice of this, it's all going to have kind of this fat lightning bolt shape. And even out here, it's that same shape, it's just smaller. If you cut it horizontally, the shapes are going to be all different, right? It's just not going to be, they're not going to be congruent shapes. So you're always going to want to cut these things so that you can find the area, and finding that area is the same. It might be a different size, but it's the same shape. So we could do that with this figure, right? We can visualize slicing it all into all these different slices. and then adding up how many slices we have and using a Riemann sum to do it, we know that the volume is just going to be the area of each slice times its thickness, and that thickness is going to be delta x, right? And then we add all those up and we go, hey, that's a Riemann sum. And I remember that if I sum up a Riemann sum where n goes to infinity, that ends up becoming a definite integral. And so it reminds us that finding volume of a shape is the same thing as finding area under a curve, where we're going to take a definite integral, and instead of the definite integral giving us area, it's now going to give us volume. So we're just kind of trying to relate this back to stuff that we already learned. Now, one thing to keep in mind is that for a cylinder, the cross-sectional area is constant. So our definition of volume can really just come down to A times B minus A, right, when we do the integration, right? And this agrees with the formula because then you just get B minus A, which is your height, right? Because you're going, when you see you're going from A to B, you're basically going from the bottom of your cylinder to the top, and so that distance is going to be the height. So this all intuitively makes sense. Now let's take a look at some examples to kind of cement it into our mind. First, we're going to look at finding the volume of a sphere. We already know the volume of a sphere is 4/3 pi r cubed. That's a formula that we should have memorized. But we can take a look at how we could calculate the volume of a sphere through slices and see that the integration actually works. So if we place a sphere at the center, right, the origin at 0, 0, and then we use a plane to slice it. Now, the nice thing with the sphere is we could really slice it in any orientation we want, and we'll always get congruent slices. But to make the math easier, you would either want to slice it horizontally or vertically. When you slice it vertically, then everything gets written in terms of x, and that's usually easier for to wrap our brains around it. But we could have also sliced it horizontally, and everything would have been in terms of y, and we can integrate in terms of y, right? That's no problem. So in this particular case, we're going to slice it vertically, and we just look at some arbitrary slice and then say, okay, can we figure out the area of that slice? Obviously, it's a circle, so we need to know the radius, right? And anywhere we slice it, it's always going to have the diagonal's always going to be the radius of our sphere. That's never going to change, right? This distance is always going to be just some amount of x, and this height is always going to be some amount y. And of course, with the Pythagorean theorem, we know that x squared plus y squared equals r squared, and then we can rewrite y in terms of r and x. So this is already giving away kind of the first major technique that we have to use when we're doing these things, and that is you always have to get your slice, the measurement of your slice, written all in terms of one variable. So you can't have x and y in there. So you have to get everything in terms of x or everything in terms of y. It just depends on which one is algebraically easier, right? And then if you want to integrate with respect to x or if you want to integrate with respect to y. So the cross section of this thing is going to be pi y squared, right? But if we want to integrate with respect to x, right, because if these are vertical slices, we have to let the vertical slices roam left and right? So we have to have a change in x. So we're going to have to integrate with dx. So we need to rewrite this in terms of x. So we just do that simple substitution. And of course, when you square root, right, you just get r squared minus x squared. Now r, remember, is just going to be a constant whenever you tell you what the sphere is. So we can leave that. We don't have to worry about, oh, we've got two variables there. R is just a constant. Now, so we set it up. We're going to integrate from minus r to r because that's how far those slices are going to roam, right? If we look back, it's going to roam all the way over here to negative r, all the way over here to r. But We need to put in the specifics for area, so we do that. And then we think, you know what? This thing is symmetrical. So instead of going from negative r to r, let's just go from 0 to r and then double it. And then pi is a constant, so we can pull that out of the integral. And now we're left with r squared minus x squared dx. We can integrate that, right? R squared is just a number, so when you integrate it, you just slap an x in front of it, right? And of course, we all know how to integrate x squared as x cubed over 3. Then we evaluate that from r to 0, and basically we just put in r and then we subtract when we put in 0, which is 0, right? So it just goes away. And if you clean that up, sure enough, we get 4/3 pi r cubed, just like we knew it should be. So here's an illustration of kind of the Riemann summiness of it, right? If we wanted to cut it into 5 disks and then 10 disks and then 20 disks, and if we actually did the approximations, we can see that it gets closer and closer and closer to 4/3 pi each time. So we know that it's a valid technique. And this is just reminding us of the Riemann sum idea of how we do that. This is all just review. You should have remembered how to do Riemann sums from long ago. Now let's get on to what we really want to talk about in this video, which is solids of revolution. Now, solids of revolution really are no different than finding area of any other solid. It's just the solid is now created by revolving some shape around an axis. Sometimes it's the x-axis, sometimes it's the y-axis, and sometimes it's a different axis, right? Any straight line in space. And depending on the line you use, well, the algebra can get a little trickier, but it's all going to boil down to a very simple concept. You just have to find the area of a slice and then take the derivative, or sorry, take the integral, right, from a to b or c to d or whatever it is of those areas. So you're just going to find cross-sectional areas either, and there it's going to be a function in terms of x or a function in terms of y. We choose which function it is depending on which direction we're integrating, right? If we're integrating with respect to x, then we need everything in terms of x, meaning our cross-sections are going to roam left and right, right? So that's why there's a change in x. We're changing in the x direction. So that means we were most likely rotating, right? We were revolving around the x-axis or some other horizontal line. If our cross sections are going to roam vertically up and down and we're going to have a change in y, then that means we rotated around a vertical axis like the y-axis or some other vertical line, and then that's why we would find the area in terms of y. So that's the only reason why you would find it in terms of one or the other. Now, if the cross section is a disk, which oftentimes it is when you spin something and then you slice it, you're just going to get a circular disk, right? Then all you have to do is find the radius, and it's some sort of formula in terms of x or y that defines that radius, square it, multiply it by pi, and there you have the area of each disk. If it's a washer, right, sometimes you'll take a shape like this and you'll rotate it around this line. So as you rotate it, you'll have this center area where there is no shape, right? And if you slice it, it looks like a washer. Well, to find that area, that's really easy. You just find the area of the larger circle and subtract the area of the smaller circle. You're basically finding the area of the disk as if it were whole, and then you're punching out that middle one, right? So it's pi times the outer radius squared minus pi times the inner radius squared. Again, you're just finding areas of circles. So you can see this whole technique boils down to finding the area of a circle, and being able to describe that radius in terms of either x or y, depending on in which direction you're going to roam. So here's our first example. We find the volume of a solid obtained by rotating around the x-axis, the region that is bounded by the curve y equals the square root of x. Now, if you aren't given pictures, try to draw a picture. Now, I know drawing three-dimensional pictures is really tough for most people, and if you can sketch something simple, go for it. But if you can't, at least draw the two-dimensional picture and give yourself a little line to kind of orient yourself and figure out, okay, so that's going to be my slice, and it just helps you visualize what's going on, and then it helps you kind of come up with the equations. So obviously, if we're slicing here, this height is always just going to be f of x, right? It's going to be the height of the function at x. So it's always just going to be the square root of x. So very easily, the area, right, is just going to be that thing squared, which is just x. You can see that we're roaming from 0 to 1. So there's our integral from 0 to 1 of pi x dx. We integrate that, we evaluate it, and we get pi over 2. It's just that simple. All right, another example. Now we're going to rotate in the other direction, right? We're going to take two shapes. I mean, it's really one shape, right? It's this curve x cubed, and then the horizontal line y equals 8. The only reason why we did that is because this function just keeps going, right? So we had to put a top on it somehow. And then we're going to spin it around the y-axis, and we get something that looks like this. Again, if you can't draw three-dimensional, at least draw this picture two-dimensional, and realize that if I'm spinning it around the y-axis, then I need horizontal slices, right? Because vertical slices would look different. If you think about slicing this thing vertically, you're just going to get these weird, odd shapes, right? Where these are just always going to be discs. That's what we're looking for. Is we always want discs and washers, right? So we always want circles and washers. Okay, well that's fine. But then how do I figure out this width, right? This width is x, but that doesn't help me because my width, sorry, my thickness is going to be delta y. That's going to be a change in y. And these things are going to roam up and down, right? So I'm going to have to integrate with respect to y. So I need to rewrite this thing in terms of y. So instead of a y equals x cubed, I have to write it as x equals the cube root of y. And now this width of x is really just a width of the cube root of y. So then we stick that into our simple formula, right? We know it's pi r squared or pi x squared, but by substitution, right? That's just the cube root of y. So it's pi times the cube root of y squared, which is just pi times y to the 2/3, right? And then we have a delta y because we're now integrating, right, with respect to y. We're roaming in the y direction. So this becomes our integral from 0 to 8, right? We start down here at 0, go up to 8 of our area function in terms of y, which is just the pi y to the 2/3 dy. We can integrate this really easily, right? Doesn't matter if it's a fraction, it's still just the power plus 1, right? Which gives you the 5/3, and then you divide by that number. So when you're dividing by 5/3, it's the same thing as multiplying by 3/5. That's where this comes from. And then we're going to integrate from 8 to 0, right? So you plug in 8, and then of course you plug in 0 and subtract that, but when you plug in 0, you get nothing. So really all that happens is you plug in 8, you do the math, and there you go. 96 pi over 5. And yes, you'd want to leave it like that, right? We leave it in terms of pi because that's a precise answer. And if you put in decimals, you're approximating. All right, how about another example where now we have something where we have to find the area in between two functions and then spin that around um, an axis. We could have spun this around the x-axis. We could have spun it around the y-axis. It doesn't matter. But the first thing you always have to do is figure out where those two functions intersect, because if you're going to take vertical slices, where do they start and where do they stop, right? What value of x do they start at and what value of x do they stop at? If you're going to take horizontal slices, right, if we spun it the other way, right? So if it was spinning around the y-axis, we would take horizontal slices to get our washers, and then it would start at a y height of 0 and finish at a y height of 1. You have to figure out these intersecting points. Now, we were given these intersecting points. If we weren't, that's where you got to do a little algebra, right? Set the things equal to each other and solve. And then from here, it's just the same thing we're always doing, right? Look at a slice, figure out how do we describe that slice in terms of our functions so that everything can be in terms of the variable that we're going to integrate. Since we're doing vertical slices and the thickness is going to be a change in x, our x's are going to roam from 0 to 1. So this outer slice, right? The outer slice is the top piece, which is equal to x, and then the inner circle is x squared. It's just that simple. So those are our two radiuses, right? Radii. So the outer one is pi x squared, and then the inner one is pi x squared squared. And then of course we can, combine those two and just have pi times x squared minus x to the fourth, stick that into our integral from 0 to 1, take the antiderivative of these things, and then go ahead and evaluate them at 1 and 0, and there's your answer, 2 pi over 15. How about we make it a little bit more difficult and we spin it around something other than an axis? So now we're going to spin something around the line y equals 2. But you're going to see that it really doesn't make it that much more difficult. All that changes is your equations for your radius is slightly augmented, right? It's still a good idea to try and draw some sort of picture, at least the two-dimensional if you could. And then you can figure out, if you drew a vertical line between the two dimensionals, that, okay, this inner radius is the distance from the line y equals 2 up to the straight line. It's kind of hard to see here, but there's a straight line here and then a curved line here, right? It's the two functions of y equals x, right? And then y equals x squared. So that inner radius, right, is this height here is going to be your first function, and then you've got a distance of 2. So all you have to do is figure out what's that overall height, right? Well, it's just f of x, right? F of x here, right? That gives me a height of x, and then that's 2. So this inner radius is just going to be the total height of 2 minus this x. That's where you get 2 minus x. And then this outer radius, same idea, right? It's this total distance of 2, but then you have to subtract this smaller bit from the outer bit, and the outer bit comes from the x squared function, right? So the height of it is f of x, and f of x is x squared. So that's where you get 2 minus x squared. So those are your two radii. It's that simple, guys. It's just a simple augmentation of the difference between the two and the function. So now we have each radius, the inner and outer, right? Or outer and inner, doesn't matter. You take the big one, subtract the small one from it. Do some algebra, right? I mean, this is all just a bunch of algebra, square some things, right? Combine like terms, get yourself a nice little simple polynomial. We can anti-differentiate polynomials all day long because we're just using the power rule, which is really simple. Then we evaluate at 1, and of course, when we evaluate at 0, everything goes away. And so even if we shifted this thing over and we were integrating from 1 to 2, it just means that at the end, we got to plug in 2, and we also got to plug in 1 and do the difference between those two, right? So it doesn't matter how much we augment these things, it all comes down to the same basic concept. You're always going to find volume by integrating from A to B, some A to some B, or some C to some D. Who cares what you call it, right? And you're going to be integrating an area. And it's going to be a function that's going to describe that area, because you're always going to take a cross-sectional slice that's going to give you either a circle or a washer. And if it's a solid disk, if it's a circle, then we know that area is just simply pi times the radius squared. You got to figure out a way to describe the radius in terms of whichever variable you're using, x or y. And that depends on if the thickness is going to be a change in x, then we do it in x. And if the thickness is a change in y, you're going to do it in y. And it all comes down to which way are you rotating? Are you rotating around a vertical line, or are you rotating around a horizontal line? And then, of course, if the cross section is a washer, then you're just taking the difference of the two, right? So you got the outer radius and the inner radius. And you can see that it doesn't matter how complicated these things get, it all boils down to just this one simple concept. And that's how we're going to tackle volumes of revolution.